We're recording. We're looking at other features of the graph. We got domain, we got range, we got end behavior, we have positive values, we got negative values, we got increasing, we got decreasing, we got local maximums, we got local minimums, and we have average rate of change. Okay, and we have zeros as well. What's another name for a zero? A root, right? And those manifest how on the graph? A root or a zero is where the graph does what? X-intercept. Yeah, they're all the same thing. Okay, so here's a story about measles, right? Not the best story about measles, but it is a story about measles. We have a graph here that we're going to start putting points. I think we read this yesterday. Let's read it again. From 74 to 80, drastic fluctuations in measles. 75, there was a slight increase, so it went up a little bit. But the next 2 years, it went up apparently even more. Reached a maximum of 26 cases per 100,000 in 1977. 77 to 79, the incidence fell to about 5. And then it fell even much faster in the next 2 years. And then finally, in the last year, it stayed about the same. So flatlined a little bit. Sketch the graph. All right. So the x-axis is important. The x-axis doesn't represent the calendar year like 1974. It's years since 1974. So right here at t equals 0 corresponds with 1974. T equals 1 corresponds with 1975. T equals 2 corresponds with 1976, so on and so forth, right? So we're establishing 1974 as our basis year. On the y-axis, we are not measuring cases of measles. We're measuring cases of measles in hundreds of thousands, all right? So let's see if we have an ordered pair anywhere. We're looking for something in the data, in the description, that gives us the number of measles at a given time. What's the first one where it does that? The actual number of measles at an actual number of time. 77, right? It said in 77, there were about 26 per 100,000. So I'm going to go to x equals 1977, and I'm going to plot the point 26. So 1977, of course, would be, if you want to keep labeling them like that, it's going to be when t equals 3, and I'm going to put about 26. So there's 25. 26 would be just above the line, right? Somewhere in there. And it's already per 100,000, so that's good. And then what does it say? Is there another point that they give us? 5 cases per 100,000 people. What year did that happen in? 79. So where would 79 be? It would be right here at t equals 5. So at t equals 5, it's going to be, we said 5. Okay, so it fell quite drastically to 5. So we'll put a solid dot right there. And that's it, right? And then it says it kind of stayed the same. So now we just kind of fill in the blanks. Did it tell us how many measles we had in 1974? No. Could it have been that there were 0 measles in 1974? Do we want to start at 0? In 1974, nobody had measles. And then all of a sudden, boom, in 3 years, it went up to 25 per 100,000. I don't know. It doesn't really tell us. Could it be that in 1974, we had some people already that had measles, we just didn't know about it? Kind of like COVID, right? Y'all lived through COVID, so we can replace measles with COVID, really. So if we read carefully, I'm not going to come in from 0 here and connect it to that. I'm going to come in somewhere over here, and then the wording should help me. From 74 to 1980, it was a drastic fluctuation. Okay, keep reading. In 75, which is right here at 1, there was a slight increase from 74. And then the next 2 years saw a substantial increase. So I want to work backwards, actually. There was a substantial increase from 1975. So as I work backwards from this point, I think I'm just going to have it dropping off kind of sharply somewhere right here. Oops, if you hold it too long, it turns into a line. I want to do it kind of as a curve, like that. And I'm just going backwards to 1975. There's really no wrong answer here if you make it a little bit steeper or a little bit less steep. But if you go now from left to right, does that look like a drastic increase to you? To me, it does. But what are we going to do now from 74 to 75? Do we continue the same steepness? No, because it said it wasn't that bad from 74 to 75. In 75, it took off. Now it's still going to be increasing, just not as quickly. So I'm going to actually curve it back the other way like this. So it kind of curves upward, and then it curves downward. We call that an inflection point. It's where the curvature changes. It curves upward like a cup, and then it curves downward like a frown. Okay, they're rising a little bit from 74 to 75, and at 75, boom, everybody with measles got together and had a party. And they said, go out and spread it. All right, now from 77, we need to keep going. The next 2 years saw substantial, which reached about, okay, from 77 to 79, which is the next two dots that we have, how are we going to connect those dots? The incidence fell to about 5 cases per 100. It didn't tell us how it fell, right? So we could just draw a line down to here, something like that. The incidence fell much faster. Oh, there's the next part. It fell much faster from 77 to 78. So let's go back and erase that. I didn't read that part. It fell much faster from 77 to 78. So I'm going to come down really fast here, like still curving down like a frown, and then somewhere there, I'm going to curve it back the other way. So we really have curvature. There's curving upwards. Here's curving downwards. And then it curves upwards again. I'm changing colors here with my highlighter. It curves upwards again somewhere in there. All the rest of the way. Okay. That's just how steep we draw it. Okay. Let me show you here with my hand. It's going up at a gradual rate, and then it goes up at a rapid rate, and then it descends at a rapid rate, and then it starts descending at a less rapid rate. It becomes less steep, kind of curving out towards maybe 0 again. And then the last little bit of information, finally from 79 to 80, the incidence stayed about the same. So what are you going to do here? You're just going to kind of keep curving it. Don't draw an absolute straight line. Just kind of keep curving it and try to make it level off to somewhere right there. All right? So there's kind of what the graph looks like. We call that concavity. I'll throw that term out at you. Like in science class, you have concave, convex. We talk about concavity of curves. It's concave up like a cup, any part of a smile, and then it's concave down like a frown, which would be any part of a frown. So it goes from concave up to concave down. It's still concave down like a frown, and then it's concave up the rest of the time, but there's a steep curve right here as it levels off. All right, so something like that. Did it ask us to do anything else with this? No, just to sketch the graph. Let's go ahead and do something else, though. Let's go ahead and do something else. If this were, in fact, a graph, what would the domain be? It would be the set of all time on the interval from, we're starting at t equals 0, and then we cruise all the way to 1980, right? 1980 corresponds with t equals what? The graph goes out to 7, but do we want to go out to 7 if the data only goes to 1980? No, 1980 only goes to 6. So sometimes you're not going to use all the graph. So our domain goes from 0 to 6. 0 to 6. And of course, we're going to put brackets there because we're going to include them. Now, the range, we can't really get the range because I don't know necessarily what the lowest number is. I'm leveling it off. It looks like it's less than 5. I don't know what it is. But if this were the graph, I could get the local maximum, can't I? You see the hill? We have a local maximum. On this interval right here, this is the high point. So we're going to have a local maximum of what? Not 25, but 26 in year 77. So at t equals 3. So let's go ahead and state that. We have a local max. And you can abbreviate maximum as max of y equals 26 at t equals 3. Or x equals 3. If you call it x instead of t, that's fine. It does say x on the x-axis. All right, what else can we do? What else can we talk about? Increasing, right? We could say this. We could say this function is increasing on the interval from t epsilon. We'll say 0 to 3. Now, I put parentheses around 0 and 3. It doesn't matter if they're parentheses or brackets. But we're going to say on this interval here, the graph is going up. If you want to say it's increasing at the endpoints, that's fine. I might just ask you to list the open intervals where it's increasing. So it's going uphill from 0 to 3. And where is it going downhill? It's still going downhill. What about at year 5? Is it still going downhill as it levels off? I would say, yeah. It doesn't go straight across, okay? That's not really reasonable. So it's still decreasing, but just very so slightly. So then we could say that this function is decreasing on the interval t epsilon 3 to 6. And remember, there's another way to say that. We could also say 3 less than t less than 6. So that's just the other way to say that. Set or interval notation. Oops. These mean the same thing. Do we have any x-intercepts? Does this graph actually touch the x-axis? Do we actually have a year where there's 0 cases? No. So there's no x-intercept. All right. All right, so that's all that one is. It's just trying to get you to think critically, and then you fill in the blanks in between. And answers can vary. All right, the key things that we're looking for are where do you change the curvature? Where do you change it from concave up to concave down? And of course, the two ordered pairs that we actually put down right here and right here, those have to be in the right spot. Kind of fun, I guess, if you like measles. Anyone here like measles? When y'all started school, y'all probably had to get a booster shot against measles and mumps. There used to be a disease called mumps. People would get mumps. Ooh, man, you got a bad case of the mumps, right? Measles, mumps, and even rubella. It's called the MMR vaccine. And y'all got that when you were young. And now we have COVID vaccines. All right, example 2. Let's move on from something so sad like measles. Let's move on to something that's even sadder. Grocery stores. Why are grocery stores sadder these days? Because with inflation out of control, grocery stores has anyone been shopping with your parents? Everything is so freaking expensive. Everything is so freaking expensive. Yeah. You try to buy like a thing of toilet paper and it's like $70 and you're like, whoa, I think I'm going back to leaves. That's how expensive it is. A grocery store stocks shelves with 100 cartons of strawberries, right? I could just see them putting them out when I go shopping every Sunday morning. They're putting out 100 cartons of strawberries. Those guys in the produce, they work hard. Oh, before the store opens. Sorry. They're doing it before I get there. For the first 3 hours the store is open, the store sells 20 cartons per hour. That's a rate, 20 cartons per hour. Does that mean that the graph is going up by 20 cartons per hour or down? Down, because they're selling them, right? They're leaving the shelf, right? Just like the candle was burning, it was getting shorter. Over the next 2 hours, though, no cartons of strawberries are sold. Oh, man. That was a bad couple of hours for strawberries, right? And then the store restocks 10 cartons every hour for the next 2 hours. In the final hour that the store is open, 30 cartons are sold. Sketch a graph of the number of cartons of strawberries that are on the shelf at any given time from t equals 0 to t equals, I guess we'll go out to 8. We'll just, since it's numbered, we can go out to 9. I guess the store is open 8 hours. And then what are we measuring on the y-axis? Actual cartons of strawberries. Not hundreds of cartons of strawberries, but actual cartons of strawberries. All right, the first thing that you want to do here is look to see if there's any ordered pairs that you can put a dot down, because those give you guidelines, right? That's what we did in the first and the last one. Do we know the number of strawberries at any given time? At t equals 0, there's how many? 100. So we can have a y-intercept of 100. I'm going to use, let's see if I have strawberry red, and I'll go to strawberry red. So right there. There's 100 cartons at t equals 0 when the store opens. For the next 3 hours, the store is open. The store sells 20 cartons per hour. So up until t equals 3, I can use my slope to go down 20, right 1. Down 20, right 1. Down 20, right 1. Are you with me? All right. So if I go down 20 from 100, that puts me at 80. And I go right 1, it puts me there. And then I go down 20 again, which is 60. And I go right 1, which is there. And I got to do it one more time. I go down 20, which puts me at 40, and I go right 1, which puts me there. Now, we can actually connect that with the solid line if you want. We can assume that they're selling strawberries at a constant rate. So far, so good. Now, over the next 2 hours, so from 3 to 5, no cartons are sold. Is that a good thing for strawberries or a bad thing for strawberries? Bad. It could be bad. If you're a strawberries, you want to be adopted to take it home. But guess what happens when you get taken home? You get eaten. So maybe it's good for strawberries that they're not being sold because they get to live. Anyone here ever been a strawberry? I don't know the perspective of a strawberry on that. Do you want to get eaten or do you want to live? All right, so for the next 2 hours, so that's from 2 to 5, no strawberries are sold. So we can connect that. That's a little horizontal line like that. Who knew strawberries would be so much fun? The store then restocks 10 cartons each hour for the next 2 hours. Now, we have to assume something here. In the next 2 hours, while the store is restocking them, we have to assume that nobody's buying them also, right? It could be, and this is one of those things that we just have to make the assumption because the problem doesn't say. But as they're restocking them while the store is open, people could also be taking them off. We're going to assume that they closed down the strawberry section. Sorry, the strawberry section is temporarily closed while we restock, okay? So we're going to put more back on the shelves, and the values are only going to go up for the next 2 hours, 10 cartons per hour. So from 5, we're going to go up 10, which is 50, and we're going to go right 1, and then up 10 to 60 and right 1. So we assume nobody is buying strawberries during those 2 hours where we close off the strawberry section. And then we open the strawberry section back up. Surprise, everybody, the strawberry section is now reopened for business. And in the final hour, okay, so it tells us we're going one more hour. In the final hour, 30 cartons are sold. So I'm going to go from 60 down to where? 30, and I'm going to go right 1. So look, boom, like that. And that's what the graph looks like. Now, if we assume that this is what the graph looks like, it's just made up of a bunch of lines, we can answer the questions about domain and range and increasing, decreasing. Let's do that. What would the domain of this function be? It would be the set of all, we'll just use x and y. It'll be the set of all x such that, let's do it in interval notation. It would be from 0 to where? 8, right? Those are the operating hours of the store. Sometimes, instead of just putting x epsilon 0 to 8, you might want to actually, if there's units, you might want to put hours after that. That kind of keeps it in the context of what we're doing. We might as well do this. We'll say, or you could say 0 less than or equal to x less than or equal to 8, right? That's the set builder notation. All right, what's the range? What y values do we take on? We'll do interval notation first. What's the smallest amount of strawberries in our graph? 30. What's the largest amount? 100. So we're going to go beefy bracket from 30 to 100, and we'll put strawberries as our units. Or, of course, you would say 30 less than or equal to y less than or equal to 100. This graph is decreasing on the interval x epsilon. For what values of x is this graph going downhill? From 0 to 3 and from 7 to 8. We haven't had one where there's two separate intervals yet. I'll show you how to join those together. If we do it in interval notation, we'll say, and I'll use open parentheses here, we'll say from 0 to 3, and then we'll say from 7 to 8, we'll leave a little space, and you know how you join them together? use a little U. This right here is called the union symbol, and it translates to the word or. That's all it means. The U without the kickstand, it's just a big old U. It means that interval or that interval. Join them together. Go ahead and write where it's increasing. It's increasing on the interval from x epsilon 5 to 7 hours. If you want to put units, you can as well. From 5 to 7. And then the last little bit where it doesn't change, guess what we call that activity? It's not increasing, it's not decreasing, it is staying the same, or as we'll call it, constant. It's constant on the interval from 3 to 5. Bless you. Do we have a local maximum? A local maximum is going to be where the graph changes from increasing to decreasing. So even though we start at 100 here, this is the absolute maximum. It's the most we ever had. It's not a local maximum because I don't know what's happening on this side. A local maximum always has to happen on a through streak. So there it is. Increasing to decreasing, we have a local maximum of 60 at 7. And that's how we write that. Okay, let's write it down. Local max of 60 at 7. So local max of 60 strawberries at the 7th hour. And I think that's it. There's no x-intercepts, are there? There was never a time where there were 0 strawberries on the shelf? Right, good. So during the 8 hours, there you go. This one we did with line segments instead of curves because this one actually gave us specific rates. We're losing 20 per hour. We're gaining 10 per hour. That's a linear rate. The one above we did with curves because it was using words like slight increase or about, right? Or kind of. Very vague terms. So we just connected them with the best we could with a curved line. All right, that concludes 2.2. Any questions? We're in here till 11:30. You have 18 minutes that you can use to finish your homework for 2.2. All right? It would be due on the next school day. Yeah. So this homework for 2.2 is due Monday at 9 a.m. And we're going to quiz Monday, remember, in class over 1.1 and 1.2. All right? Okay. Y'all can feel free to move about the cabin, as they say.